Yes, a voltage of 290 volts can be lethal, especially if the current is sufficient. In dry conditions, a current as low as 50 milliamps or 0.5 amps can cause ventricular fibrillation, which is a potentially fatal heart rhythm. Yes, the electrical contractor could potentially be held liable if someone gets a shock from the gutter because, firstly, negligence. The contractor failed to recognize and address the stray voltage hazard, which was a foreseeable risk. Secondly, breach of contract. If the contractor was hired to ensure the safety of the electrical system, they may be liable for failing to do so. Thirdly, strict liability. In some jurisdictions, manufacturers or installers of products that cause injury can be held strictly liable, regardless of negligence. To mitigate the risk of stray voltage, the following measures should be considered. Firstly, grounding. Grounding the gutters with a properly sized grounding rod, as the electrician did, can help to dissipate the stray voltage and prevent shocks. Secondly, shielding. Installing a metal shield between the gutters and the transmission line can help to block the electromagnetic field and reduce stray voltage. Thirdly, use of low voltage systems. For gutters and other exposed metal components, using low voltage systems, for example 12 volts, can reduce the risk of shocks. Fourthly, regular maintenance. Regularly inspecting and testing the grounding system and other safety measures is essential to ensure continued protection. Additional precautions: the electrical contractor should ensure that the grounding system is permanently installed and maintained. Warning signs should be posted to alert people to the potential hazard. The contractor should document all actions taken to mitigate the stray voltage risk. By taking appropriate precautions, the electrical contractor can minimize the risk of liability and ensure the safety of the building occupants. The presence of stray voltage from a high voltage transmission line introduces several electrical engineering concepts. Firstly, capacitive coupling. The high voltage line creates an electric field. Metallic objects like gutters within this field can accumulate charge through capacitive coupling. This is similar to how a capacitor stores energy. The amount of voltage induced depends on the strength of the electric field, the size and shape of the metallic object, and its distance from the source. Secondly, inductive coupling. The transmission line also generates a magnetic field. This field can induce current in nearby conductive loops, like the gutter system. This phenomenon is governed by Faraday's law of induction. The magnitude of the induced current depends on the strength of the magnetic field, the area of the loop, and the frequency of the alternating current in the transmission line. Thirdly, grounding and bonding. Grounding provides a low impedance path for stray currents to return to the source, typically the earth. Bonding ensures that all metallic parts are electrically connected, minimizing potential differences and reducing the risk of shock. A properly sized grounding electrode system, such as an 8-foot ground rod, is crucial for dissipating stray voltage. The effectiveness of the grounding system depends on the soil resistivity. Lower soil resistivity provides better grounding. Fourthly, voltage and current relationship. Ohm's law, voltage equals current times resistance, dictates the relationship between voltage, current, and resistance. Even a relatively small voltage can produce a dangerous current if the resistance is low enough. In the case of the gutters, contact with a person provides a path to ground, potentially resulting in an electric shock. Fifthly, lethal current levels. The human body's reaction to electric current varies depending on factors such as the current's magnitude, frequency, path, and duration. As little as 50 milliamps or 0.5 amps can cause ventricular fibrillation, a life-threatening heart rhythm. Higher currents can cause burns, muscle contractions, and respiratory arrest. Sixthly, safety standards and codes. The National Electrical Code, or NEC, provides guidelines for electrical installations to ensure safety. Article 250 of the NEC covers grounding and bonding requirements. These requirements are designed to minimize the risk of electric shock and fire. Local codes and regulations may also apply. Seventhly, mitigation techniques. Besides grounding, other mitigation techniques include shielding, which involves placing a conductive barrier between the source of the electromagnetic field and the affected object. This barrier reduces the electric and magnetic fields reaching the object. Another technique is using low voltage systems, which reduces the potential for dangerous shocks. Regularly inspecting and maintaining the grounding system is also crucial to ensure its effectiveness. Eighthly, risk assessment. Assessing the risk of stray voltage involves identifying potential sources, measuring voltage and current levels, and evaluating the potential for human contact. This assessment should be conducted by qualified professionals with expertise in electrical safety. The electrical contractor's liability stems from several factors. Firstly, negligence. If the contractor failed to exercise reasonable care in identifying and addressing the stray voltage hazard, they could be found negligent. This includes failing to follow industry standards and best practices. Secondly, breach of contract. If the contractor's contract included a provision for ensuring electrical safety, they could be liable for failing to meet this obligation. Thirdly, strict liability. In some jurisdictions, contractors may be held strictly liable for injuries caused by their work, regardless of negligence. This is particularly true if the work involves inherently dangerous activities. The contractor can take several steps to minimize their liability. Firstly, conduct a thorough site assessment to identify potential hazards. Secondly, implement appropriate mitigation measures, such as grounding and shielding. Thirdly, document all actions taken to address the stray voltage issue. Fourthly, provide warnings to building occupants about the potential hazard. Fifthly, obtain adequate insurance coverage to protect against potential claims. The long-term grounding solution must consider corrosion, physical damage, and changes in soil conditions. Periodic testing of the grounding system's resistance is necessary to ensure it remains effective. Alternative grounding methods, such as ground grids or chemical ground rods, may be considered in areas with high soil resistivity. The utility company's involvement is crucial in addressing stray voltage issues related to transmission lines. They have the expertise and equipment to assess the problem and recommend appropriate solutions. Communication and coordination between the contractor, the utility company, and other stakeholders are essential for ensuring a safe outcome. From an engineering perspective, several calculations and measurements are necessary to properly address the stray voltage issue. Firstly, calculate the induced voltage using formulas based on capacitive and inductive coupling. These formulas take into account the voltage and current of the transmission line, the distance to the gutters, and the geometry of the system. Secondly, measure the voltage and current on the gutters using appropriate test equipment. These measurements should be taken under various conditions to assess the worst-case scenario. Thirdly, calculate the required grounding electrode size based on the fault current and soil resistivity. The NEC provides guidelines for determining the appropriate size of the grounding electrode. Fourthly, verify the effectiveness of the grounding system by measuring the ground resistance. This measurement should be taken using a ground resistance tester. The grounding system should be designed to maintain a low ground resistance, typically less than 25 ohms. Fifthly, perform a step and touch potential analysis to assess the risk of electric shock. This analysis involves measuring the voltage gradient around the grounding electrode. The step and touch potential should be below safe levels, as defined by industry standards. The risk assessment should consider the following factors. Firstly, the likelihood of human contact with the gutters. Secondly, the severity of potential electric shock. Thirdly, the effectiveness of mitigation measures. Fourthly, the potential for equipment damage. The risk assessment should be documented and updated regularly. Warning signs should be placed in prominent locations to alert people to the potential hazard. These signs should clearly state the nature of the hazard and provide instructions on how to avoid it. The electrical contractor should provide training to workers and building occupants on the dangers of stray voltage and how to respond in an emergency. This training should include information on how to recognize the signs of stray voltage and how to avoid contact with energized objects. The electrical contractor should develop an emergency response plan to address potential incidents involving stray voltage. This plan should include procedures for shutting off power, providing first aid, and contacting emergency services. The electrical contractor should maintain detailed records of all actions taken to address the stray voltage issue. These records should include site assessments, measurements, calculations, mitigation measures, and training programs. These records can be used to demonstrate due diligence and protect against potential liability claims. The electrical contractor should consult with legal counsel to understand their potential liability and develop strategies to minimize their risk. Legal counsel can provide guidance on contract provisions, insurance coverage, and other legal issues. The electrical contractor should stay up to date on the latest industry standards and best practices for addressing stray voltage issues. This includes attending training courses, reading technical publications, and participating in industry organizations. By staying informed, the contractor can ensure that they are using the most effective methods for mitigating the risk of stray voltage. In addition to the technical and legal aspects, it is also important to consider the ethical implications of the stray voltage issue. The electrical contractor has a responsibility to protect the safety of the public and to act in a responsible and ethical manner. This includes being transparent about the risks of stray voltage and taking all necessary steps to mitigate those risks. The electrical contractor should also be willing to work with the utility company and other stakeholders to find a solution that is both safe and cost-effective. The stray voltage issue highlights the importance of proper electrical design, installation, and maintenance. It also underscores the need for ongoing education and training for electrical contractors and other professionals involved in the electrical industry. By working together, we can ensure that electrical systems are safe and reliable for everyone. The presence of a 345 kV transmission line introduces several challenges related to electromagnetic interference, or EMI. The high voltage and current in the transmission line generate strong electric and magnetic fields which can induce voltages and currents in nearby metallic objects, such as the gutters. The magnitude of the induced voltage and current depends on factors such as the distance from the transmission line, the orientation of the metallic object, and the frequency of the power line current, which is typically 60 Hz in North America. The induced voltage and current can pose a safety hazard to people who come into contact with the metallic object, as well as interfere with the operation of electronic equipment. Several methods can be used to mitigate EMI from transmission lines. Firstly, increasing the distance between the transmission line and the metallic object. The further away the object is from the transmission line, the weaker the electric and magnetic fields will be. Secondly, shielding the metallic object with a conductive material. This can reduce the amount of electromagnetic energy that reaches the object. Thirdly, grounding the metallic object to provide a path for the induced current to flow to ground. This can reduce the voltage on the object and minimize the risk of electric shock. Fourthly, using filters to block the EMI from entering electronic equipment. These filters can be installed on power lines or signal cables. Fifthly, using twisted pair or shielded cables to reduce the amount of EMI that is radiated or received by the cables. It is important to note that EMI can also be caused by other sources, such as radio transmitters, cell phones, and electronic equipment. Therefore, it is important to consider all potential sources of EMI when designing and installing electrical systems. The NEC provides guidelines for minimizing EMI in electrical systems. These guidelines include requirements for grounding, bonding, and shielding. The NEC also requires that electrical equipment be tested to ensure that it meets EMI standards. In addition to the NEC, other standards, such as those developed by the Institute of Electrical and Electronics Engineers, or IEE, provide guidance on mitigating EMI in electrical systems. These standards cover topics such as grounding, shielding, and filtering. Mitigating EMI is an important part of ensuring the safety and reliability of electrical systems. By following the guidelines and standards provided by the NEC, IEE, and other organizations, electrical contractors can minimize the risk of EMI and protect people and equipment from its harmful effects. The NEC Section 250.4 addresses the general requirements for grounding and bonding. It emphasizes the need for an effective ground fault current path, which is essential for the proper operation of overcurrent protective devices like circuit breakers and fuses. The goal is to ensure that a fault to ground will quickly create a high enough current to trip the breaker or blow the fuse, thus disconnecting the circuit and preventing a sustained shock hazard. NEC Section 250.24 covers grounding service supplied alternating current system. It requires a grounding electrode system to be connected to the grounded conductor, typically the neutral, at the service equipment. This grounding electrode system can consist of various elements, such as a metal underground water pipe, a ground ring, or ground rods. The goal is to provide a low impedance path to ground for fault currents. NEC Section 250.50 and 250.52 detail the requirements for grounding electrodes. These sections specify the types of electrodes that are permitted, such as ground rods, ground plates, and concrete encased electrodes, and the minimum requirements for their installation. For example, ground rods must be at least 8 feet long and driven into the ground to a certain depth. The type and number of grounding electrodes required will depend on factors such as soil resistivity and the size of the electrical system. NEC Section 250.166 covers sizing the grounding electrode conductor for alternating current systems. The grounding electrode conductor connects the grounding electrode to the grounded conductor at the service equipment. Its size is determined based on the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor for different sizes of service entrance conductors. NEC Section 250.92 covers bonding equipment containing service conductors. It requires that metallic enclosures containing service conductors be bonded together into the grounded conductor at the service equipment. This bonding helps to minimize voltage differences between metallic parts and reduces the risk of electric shock. NEC Section 250.96 covers bonding other enclosures. It requires that metallic enclosures that are likely to become energized be bonded together into the grounding system. This includes enclosures for equipment such as motors, transformers, and panel boards. The bonding helps to create a low impedance path for fault currents and reduces the risk of electric shock. NEC Section 250.104 covers bonding of piping systems and exposed structural steel. It requires that metallic water piping systems and exposed structural steel that are likely to become energized be bonded to the grounding system. This bonding helps to prevent these systems from becoming energized and creating a shock hazard. NEC Table 250.122 provides guidance on sizing equipment grounding conductors for grounding raceway and equipment. The size of the equipment grounding conductor is determined based on the size of the overcurrent protective device protecting the circuit. The table specifies the minimum size of the equipment grounding conductor for different sizes of overcurrent protective devices. In the situation described, where stray voltage is detected in the gutters, it's crucial to ensure that the grounding and bonding system is properly installed and maintained according to the NEC requirements. The electrician's action of installing a ground rod to the gutters was a good first step, but it's important to verify that the grounding system meets all applicable NEC requirements and that it effectively mitigates the stray voltage hazard. It's also important to investigate the source of the stray voltage and take steps to eliminate it if possible. The utility company's assessment that the 345 kV line is the source suggests that induced voltage is the likely cause. In such cases, shielding or other mitigation measures may be necessary in addition to grounding and bonding. The electrical contractor should consult with a qualified electrical engineer to develop a comprehensive plan for addressing the stray voltage issue and ensuring the safety of the building occupants.